Hello viewers, in this video we are going to learn about the execution of memory reference instructions in a basic computer. Before going to learn about the different operations which are performed by the memory reference instructions, let us have a look into its instruction cycle. In the first phase of its instruction cycle, the memory reference instruction is fetched from the memory and it is loaded into the instruction register. During this phase, the timing signals T0 and T1 are required. Okay, after this phase, the instruction needs to be decoded. Okay, decoding of the instruction is very important because at the end of the decode phase only, the control unit will come to know what operation need to be performed. Based on that, it will initiate the control signals in order to perform micro operations by various units of the computer. Okay, this decode phase is performed when timing signal T2 is active. Okay, when decode phase is performed, this 12 to 14 bit of the instructions are decoded by the 3 by 8 decoder, and based on the input values, this decoder it will activate one out of 7 output lines which are designated with T0 to D6. Usually the memory reference instruction it takes the input values in the range 000 to 110, right? So based on its input values, one out of 7 output lines will be activated. Whereas coming to the 15th bit of the instruction, if it is equivalent to 0 during the decode phase, it will be received by the I flip-flop. So now I flip-flop value also will be 0. Okay, coming to the 0 to 11 bit of the instruction, it will be received by the address register during the decode phase. Okay, when 15th bit equal to 0, the address that is received by the address register, it will be a effective address of the operand. If 15th bit of the instruction equal to 1, then I flip-flop value also will be 1. Then if 15th bit equal to 1, the address part of the instruction it contains the indirect address. Okay. So during the decode phase, the address register it will receive the indirect address of the operand. Okay. So in the next timing signal D3, the effective address of the operand need to be read from the memory, from the location that is pointed by the address register, and it has to be loaded into the address register. Now, at the end of the timing signal T3, the address register might be holding the effective address of the operand. And this phase is applicable only for the memory reference instruction which contains the indirect address in its address part of the instruction. Okay, so after this phase, the instruction execution shall start when timing signal T4 is active. Since instructions are being executed, the memory unit is referred either to read the input operand or to write the result of the operation to the memory unit or for performing both. That's why these instructions are known as memory reference instructions. As well, memory reference instructions are being performed by ALU unit, right? So, it is very important to understand how this ALU unit and memory unit are connected together in a common bus system. Okay, let us have a look into the ALU unit first. Okay, here, just look at the common bus system in the ALU unit. It takes three inputs. One input is from the data register, and another input is from the accumulator, and another input is from the input register. Okay, so this ALU unit can receive operands from either any one of these three registers only. Okay, and how come whenever it needs to receive any data from the memory unit, how come it can receive? Let us check. Okay, is there any direct path from the memory unit to the ALU unit? No, there is no direct path. So, if operand is required from the memory unit, first that operand need to be transferred to the data register during the timing signal T4. Okay, so once it is transferred to the data register, in the next timing signal T5, the ALU unit can perform its operation by taking that operand which is right now available in the data register. Okay, this is how Any data can be received by the ALU unit whenever required. First, it is transferred to the data register, and then the ALU unit receives that data and it performs the operation. Let us now discuss the AND operation, which is performed when D0 output of the decoder is active. This AND logic operation is performed by taking one of the operand from the accumulator and another operand from the memory unit whose address is pointed by the address register. And after performing the AND logic operation, the result is loaded into the accumulator. And this AND logic operation is performed by performing two micro operations in two clock signals. Okay, since one of the operand is taken from the memory unit, as we just discussed, since there is no direct path to receive the content from the memory unit to the ALU unit, first during the timing signal T4, the content need to be transferred to the data register. Okay, the operand value that need to be read from the memory unit whose address is pointed by the address register, and it has to be loaded into the data register. In order to achieve this data transfer from memory unit to data register, the control unit has to set the selection signal values to 111 and it has to activate the read signal of the memory unit also. And to receive the data, the load signal of the data register must be enabled. Okay, and after this data transfer, during the timing signal T5, now this ALU unit can perform the AND logic operation by taking one of the operand from the accumulator and another operand which is available in the data register, and after performing the operation, it loads the result into the accumulator. And at the end of the each memory reference instruction, the sequence counter value need to be cleared in order to initiate the timing signal from T0 for the execution of the next instruction in sequence in the next clock cycle. Okay. Coming to the add operation, this is performed when D1 output of the decoder is active, and for this addition operation also one of the operand is taken from the accumulator and another operand from the memory unit from the address pointed by the address register, and the sum value is transferred to the accumulator and the carry is sent to the extended bit accumulator. Okay, since here also one of the operand is taken from the memory unit, first during the timing signal T4, that content need to be transferred to the data register, and in the timing signal T5, the addition operation can be performed by taking one of the operand value from the accumulator and another operand from the data register, and after performing the addition operation, the sum is transferred to the accumulator and carry is transferred to the extended bit accumulator. Okay, at the end the sequence counter need to be cleared. Okay, coming to the load memory word to accumulator, this operation is performed when D2 output of the decoder is active. Okay, here to load the memory word to the accumulator, the memory word need to be read from the memory unit from the address that is pointed by the address register, and it has to be transferred to the accumulator. Okay, so to perform this data transfer, let us check, is there any direct path from memory unit to the accumulator? Is there any direct path from the memory unit to the accumulator? No, there is no direct path. So, to transfer the memory word from the memory unit to the accumulator, first during the timing signal T4, that memory word need to be transferred to the data register, and in the next timing signal T5, that memory word which is right now available in the data register, that can be transferred to the accumulator. Okay, you can observe here during the timing signal T4, the memory word is read from the memory unit whose address is pointed by the address register, and it is transferred to the data register. Okay. Then during the timing signal T5, now the content which is right now available in the data register is transferred to the accumulator. This is how the content from the memory unit can be transferred to the accumulator. Okay. And coming to the store accumulator to the memory word, this operation is performed when D3 output of the accumulator is active. And to transfer the content from the accumulator to the memory, is there any direct path? Yes. From the accumulator to transfer any content to the memory unit, there is a direct path is available. So, this data transfer can happen within a single clock cycle. Okay, when T4 timing signal is active, the content can be transferred from the accumulator to the memory unit to the address pointed by the address register. Okay, for achieving this, the selection signal values need to be 100 and the write signal of the memory unit need to be enabled. Okay, since there is a direct path, this operation is achieved in a single clock cycle, you can notice. Okay. According to the branch unconditionally operation, it is performed when D4 output of the decoder is active, and this operation is performed in order to transfer the program execution control to the address that is pointed by the address register. Okay, so when the address is transferred to the program counter register, in the next clock cycle, the instruction whose address is available in the program counter will be executed. Okay, so like this, the branch unconditionally operation achieves the transfer of program execution control to the address that is pointed by the address register. Okay, so this operation is achieved during the timing signal T4. Okay, since there is a direct path is available from the address register to the program counter register, this can be achieved in a single clock cycle. Okay, to achieve this data transfer, the selection signal values need to be 001 and the load signal of the program counter must be activated. Coming to the branch and save return address, it is executed when D5 output of the decoder is active. This branch and save return address operation is performed in order to transfer the program execution control to the subroutine call. Okay, let us now check how this operation is performed through the micro operations of various components in a computer. Okay, when D5 output of the decoder is active and the T4 timing signal is active, the control unit transfers the content in the program counter to the memory unit to the address that is pointed by the address register. Okay, and at the same time, during the clock cycle, the address register content also incremented. Okay, here you can notice the content of the program counter is stored into the memory unit to a particular address that is pointed by the address register. This address that is transferred to the memory unit, this is the return address. This is the return address. That is, after executing the subroutine, the program execution control should come back to this address and it has to resume the program execution. So, after the execution of the subroutine, it has to come back to the main program, right? So, it is possible if it stores the return address to memory unit to the address that is specified in the address part of the instruction. Okay, and in the same clock cycle, during the timing signal T4, the address register content also need to be incremented. That incremented value of the address register is the address of the first instruction in the subroutine. Okay, that incremented value of the address register need to be transferred to the program counter register during the timing signal T5. Okay, so from the next clock cycle onwards, the instructions in the subroutine can be executed sequentially until the written statement of the instruction is met. Okay, let us now check how these micro operations are performed in the content of the memory program counter address register, which are indicated during the timing signal T4. How these operations are performed on these components, let us check. Okay, in the location in the memory location 20, you can observe the memory reference instruction which performs the branch and save return addresses stored. When this instruction is executed, what happens? The program counter value 21, it has to be stored into the memory to the address that is pointed by the address part of the instruction, right? So this 21, which is the return address, it has to be stored into the address that is specified in the address part of the instruction. Okay, after this, what has to be done? The address value need to be incremented. So the address register value need to be incremented. When it is incremented, it will be 136. So now this incremented value need to be transferred to the program counter in the next timing signal. Okay. So now in the next timing signal, the program counter register received the incremented value. So, in the next clock cycle onwards, the execution of the subroutine will take sequentially one by one. Okay, until the return statement of the subroutine is met. If suppose usually the last statement of the subroutine be the return statement, right? You can see the instruction which performs the branch and conditionally operation is included at the end of the subroutine. Usually here a return statement will be there, right, at the end of the subroutine. So in this place, in order to return from the subroutine to the main program, this instruction which performs the branch and conditionally is included. In this, in the address port 135 is there, this address is the indirect address because the mode bit value equal to 1. Okay, so to return back to the main program, the address of the instruction from where it has to resume it is required, right? So that address can be found if the control unit goes to this indirect address. If it goes to this indirect address 135, it can find out that effective address from where it can resume its execution. Okay, this is how branch and save return address. It transfers the program execution control from the main program to the subroutine, and after executing the subroutine and at the end of the return statement, it transfers again back to the main program. Okay, coming to the next operation, increment and skip if 0. This is performed when D6 output of the decoder is active. Okay, this operation, it increments the memory word. What it increments? It increments the memory word. If the incremented value is equivalent to 0, then it skips the next instruction. Okay, you can look at the symbolic description of this operation. First, the memory word which is stored into the memory unit whose address is pointed by the address register is incremented. Okay, if the incremented value equal to 0, then the next instruction is skipped by incrementing the program counter value. Okay, just let us have a look into the micro operations which are performed in order to achieve this operation. Okay, here before looking into this micro operation, have a look into the memory unit. Okay, in this operation, the memory word need to be incremented, right? So, is there any provision in the memory unit in order to increment its content? No. There is no provision for incrementing the value of the memory words in the memory unit. Okay. So, in order to increment the value of the memory words which are stored in the memory unit, first it has to be transferred to the data register during the timing signal T4, and in the next timing signal T5 it can be incremented because in the data register there is a provision for incrementing the content because it has the increment signal. Okay, so by enabling the increment signal, the content can be incremented in data register during the timing signal T5. During the timing signal T6, the incremented value which is available in the data register is returned to the memory unit. If that value is equivalent to 0, then the program counter value is incremented. Okay, at the end of the instruction execution, the sequence counter value need to be cleared. This is how the 7 different operations of the memory reference instructions are executed. Students, if you find this video useful to you, kindly subscribe this channel. Thanks for watching.